The last solar technology we're going to talk about is solar thermal power systems. So we've previously talked about solar photovoltaics, which directly convert the energy of photons of light into electricity. Then solar heating, which is just sunlight warms something up. It can warm up your house. It can warm up water that you put into your pool. It can warm up fluid that you use to heat the water that you use for showers in your house. Solar thermal power has that word thermal in it, but it's used to create electricity, and it creates electricity in a different way than solar photovoltaic does. We saw that we make electricity from fossil fuel power plants and nuclear power plants by boiling water. Well, we can boil water with sunlight as well. We have to concentrate the sunlight to a smaller area, just put a cup of water outside, it's not going to start boiling. But if I put mirrors all around and I focus all the sunlight on that cup of water, then I can get it to boil. And if I've got that boiling water, I can use that as steam to spin a turbine connected to a generator and make electricity that way. So the figure here shows just schematic of a couple of different ways you can uh, concentrate sunlight on a smaller area to superheat a fluid. And it can be water, but it usually isn't water. Uh, Here's another different type of concentrator where you don't have to have everything landing exactly on a single point. So this allows the sunlight to be coming in from any different direction. I don't have to be pointing this thing, and I can concentrate sunlight at some level, but not as great a level as I would with this sort of telescopic setup here, where my mirrors are pointed at the sun and all of the sunlight is really directly concentrated at one point. So here are some examples of these things. Uh, Here are some small uh, collector dishes, and all of these points on each of these dishes are reflecting sunlight up to the devices at the focus of the dish, where there is a fluid that is heated up, and as it gets very hot, it evaporates and drives a piston inside a cylinder, which is used to generate electricity. A larger scale system uses molten salt as a heat transfer liquid, and the reason for that is that can get to a higher temperature without evaporating. So I can store more thermal energy in liquid salt system than in liquid water. The water, once it gets to 100 degrees Celsius, it evaporates and evaporates, it expands dramatically, it becomes steam, and that makes it more difficult to keep contained. So here you've got a number of mirrors, and these mirrors are focusing the sunlight at the tip of a tower there. Here's another view of a system with 350,000 mirrors that are directing sunlight at this tower. And it's possible, since this mentions three towers, that I actually saw that, because this is a picture that I took uh, in Southern California when I was flying home from Los Angeles on a flight. Looked outside, and here you see three uh, arrays of mirrors that are concentrating sunlight on towers. You can see those little towers as little vertical dark marks in the centers of those things. And so the characteristic of all of these plants, all of these facilities that I'm showing you here, is that they concentrate sunlight onto a fluid, superheat that fluid. You use that fluid either to transport it over to steam or to directly drive a piston, and you make a turbine spin and generate electricity the same way you do in a fossil fuel power plant. So we drive turbines with steam, but we can create steam by concentrating sunlight in a small area. So that's another kind of technology that can be used to generate electricity from sunlight. Finally, let's talk about environmental impacts of solar energy. Solar photovoltaic cells, you got to build those cells, so that takes some energy. I've got to go get the materials to create those photovoltaic cells. It's special materials. I have to build it, I have to transport it and install it. That takes some energy. Theoretically, hypothetically, it could be possible that the amount of energy it takes to make a solar panel is greater than the amount of energy I get from the solar panel before it breaks down. Happily, that's not the case. Typical lifetime for solar panels is measured in decades, 20 to 30 years. Of course, the technology is always improving, so we don't know for the ones that are being made today or the ones that are on the roof of my house that are a couple years old, if they're going to last 20 years or 40 years. But expectation is decades, and the energy that is produced by those panels in 2 years, and now with improvements since this figure was made, it's less than 2 years, is enough to build a new panel. And so this is just a kind of sanity check that says that they are environmentally and energetically sensible. It takes a small fraction of the total lifetime of the panel to generate enough energy to make another panel. So if we were imagining that we get all of our energy from solar photovoltaic, and I just started with only solar photovoltaic, I can take the energy from them to make more of those panels, and I will still have energy left over. So the payback time, based on the data from when your book was published a few years ago, was about 2 years. So that's a sanity check. There are other ways, the factors that we have to think about with solar power in terms of storage. And so you may have heard about hydrogen as a fuel source and fuel cells. Fuel cell uses hydrogen. The problem with hydrogen as a fuel source is that we can't just go get hydrogen. We have to use energy to make it. And in that sense, hydrogen is really like a battery. It's a way to store energy. So we can use electricity that we get from the sun to split water molecules into hydrogen and oxygen. Then we can put that hydrogen in a tank, and now we've got a fuel that was made from sunlight. And when we burn that fuel, we produce water, which is clean. And so that's the value of hydrogen. But I'm hesitant to use the word fuel for hydrogen because that suggests that we could go dig some up somewhere. We have to put the energy in to get the hydrogen. So it's a storage technology really more than a fuel itself. So the cost of solar photovoltaics has been coming down, and that has played into, as well as policies have played into the rapid growth in the deployment of solar photovoltaic that we saw earlier in the module. Costs are now down around $3 a watt for installed solar photovoltaic capacity on a residence in the United States. That means a 10 kilowatt system costs about $30,000 or so. That's projected to drop by maybe another 30 to 40% in the next 10 years. And as a comparison, the cost of a kilowatt hour of energy is about 13 cents. And so I can take a look at the solar power coming from my system on my house right now. I can tap into an app and it'll show me how much power is coming from it. So this is my current home system monitor, and it's currently producing 6 kilowatts of power, and lifetime it's showing 26 megawatt hours of energy in less than 2 years. And a megawatt hour is 1,000 kilowatt hours. So that's 26 1,000 kilowatt hours, and a kilowatt hour is about 13 cents. So that's about $3,000 of electricity that's been generated by that system. So the economics of solar photovoltaics are banks typically provide a loan, and the cost of paying off that loan equals the cost of your electricity savings that you're no longer paying to the utility.